Hi everyone, welcome back. Today we're going to learn about energy and enthalpy. Pause the video for a moment and read over the learning objectives so you have a better understanding of the things that we expect you to be able to do. So let's first talk about what energy is. Energy is the capacity or ability to do work and to transfer heat. In other words, it's the ability to get things done. And energy comes in multiple forms. You've heard of potential energy and kinetic energy, and all types of energy can be classified into one of those two categories, either potential or kinetic energy. So let's give a scenario here. So let's say that you have a ball rolling on a flat surface heading towards a hill. Because it has movement, we would call that kinetic energy. Potential energy has to do with the ball's relative position to another object. So we might talk about its relative position to this surface. And right now it has very little potential energy because it's on the surface. It's on that flat surface. And so we have high kinetic energy because it's moving quickly, and low potential energy. As the ball goes up the hill, it begins to slow down. And the kinetic energy goes down, and the potential energy goes up because its position relative to that surface is increasing. When it gets to the top of the hill, its kinetic energy is as low as possible without stopping in any case, and its potential energy is the highest. As it goes down the hill, then those forms reverse again. And so what we see here is that these two forms, kinetic and potential energy, are changing between each other. And this brings us to what's called the first law of thermodynamics. And that is that energy cannot be created or destroyed, but is only converted between forms. Today we're going to talk about two types of energy. We're going to focus on electrostatic potential energy, and we're going to look at heat, or enthalpy, as well. Electrostatic potential energy, also referred to as electrical potential energy, has to do with when you have charged particles that are separated by a distance. So what we see here, this is called Coulomb's law. And Coulomb's law describes the energy that is between any two charged particles. You're not going to need to calculate specific energies, but only relative energies. So this constant K here, we're never going to need you to use. Rather, you're going to solve using the various charges and the distance between those charges. So let's say we have a scenario where we're looking at charges. This is how we might plot it. If we have two positive charges or two negative charges, they will repel each other. You've heard the term opposites attract, and that's the case when it comes to charges. In this case, they're repelling each other because they are similar charges. And as we increase the distance between them, they repel less and less, and therefore the energy goes down. If we have two opposite charges, then they're attracted to each other, and they have very low energy. As we increase the distance between them, the attraction gets weaker, and so the energy goes up. In both cases, we see that the energy approaches zero. The energy goes to zero as the distance increases. And we can see that here. If the denominator here gets large, then that means that the magnitude of our energy is going to go down, and it's going to approach zero. Let's look at an example here. This is something that you might see on a homework or an exam. We have three sets of charged particles, and we want to rank them. The way we would do this is by using Coulomb's law. Again, we see in this case that they are separated by the same distance. And so this is going to be a constant, as will the proportionality constant. These two values are constant. So the only thing that matters is the values and the signs of our charges here. So this one way you could solve this is by doing the following. You have your equation and substitute in the charge values. It doesn't matter which one, if you say the value on the left goes on the left here or on the right, it's on the right. Because we're taking the product, then it won't matter. So we've substituted in the charges. K and D are constants, and so when we solve and simplify, we get -1 times K over D. For the second system, we have a -3 and a -1. When we plug those values in, they multiply and we get +3 times K over D. For the third system, we have -2 and a +1. When you multiply those two together, you get a -2. And what I would recommend that you do at this point is make a number line. We're wanting to determine the order of these in terms of increasing electrostatic potential energy. And if you plot these on a number line, placing them centered around 0, we can see that we have one of them at a value of -1, one of them at a value of -2, and one at a value of +3. So set number 1 is at -1 K over D. Set number 2 is at +3. And set number 3 is at -2. And since these are increasing from left to right, and we want to place them in increasing order, we can simply set the inequalities. And we see that 3 is less than 1, which is less than 2. And that gets us E as our final answer. We're going to leave electrostatic potential energy for now, but we will revisit it a lot during the semester. So it's important that you understand how to solve problems like these. Let's now talk about systems and surroundings. In chemistry, what we pay attention to, the chemical reactions, those make up our system. And everything else is what we call the surroundings. So if you're doing a chemical reaction, say that you've got water and you're putting in a salt into it and they dissolve. That chemical reaction is our system. Everything else, the thermometer, you, the beaker, that makes up the surroundings. And that becomes very important because when we measure temperatures, we're measuring it from the perspective of the thermometer or from the surroundings. And so we care about internal energy because the higher energy a system is, the more reactive it is, the more unstable. Low energy means that our system is stable. High energy means that it is unstable. And so in order to predict how reactive something will be, if we know something about its internal energy, then we can know how reactive it might be. We talk about changing states. If we go from a high initial state to a low initial state, then we've given off energy. We lose energy to our surroundings. Delta E is less than 0. But if we went from a low initial state to a high final state, then we've gained energy from our surroundings, and that means that the energy of the reaction is greater than 0. And again, we can divide those types of energy into potential or kinetic, electrostatic potential energy, heat. What's important right now is to realize what is our system and what is our surroundings. Internal energy we can think of as involving heat and work. And We can lose energy to the surroundings in terms of heat exiting the system or work being done by the system. We can have heat enter the system and work done on the system, and that's energy gained. Or we might have scenarios where heat exits the system, but the system also does work. Or excuse me, where work is done on the system. Or you might have a scenario where heat enters the system, but the system does work. And so it turns out that the signs and the magnitudes of energy, including the units, whether it's kilojoules, whether it's joules, whether it's millijoules, etc., those are important to pay attention to. And so in solving problems, you're going to want to know what units are involved. Is heat entering the system? Is it exiting the system? We always look at things from the perspective of the system, and so that's how we want to define it. So internal energy. Let's talk a little bit more about internal energy. It's what we call a state function, and state functions do not depend on the path or the method that's used to obtain that state, but only what the initial and the final states are. So for example, if we look here, we could take boiling water and cool it down to room temperature. Or we could take ice and melt it and increase it until it gets to room temperature. These two processes took different paths, but they, in the end, ended up at the same final state. Same mass, same temperature, which means that they both have to have the same internal energy. This principle becomes very important later down the road when we look at chemical reactions. For now, what you want to realize is that state functions only depend on what current state they're in, and some examples of state functions include temperature, pressure, and enthalpy. Heat and work are not state functions, so the amount of heat given off or absorbed depends on the process, the path that's taken. Same thing for the amount of work. Let me give you a macroscopic or a real-world, more concrete example of state function, and that's elevation. So as I said before, state functions only depend on your current state. Hence the term state function. And elevation is one example of that. If we start here at the bottom of this path, and we go and we climb like a mountain goat up this mountain, go up to the top, we end right here. Or we take the more roundabout path. Both of those, as long as we end in the same spot, are at the same elevation. It doesn't matter which path we took. What does change, however, is the distance that you traveled. So the distance traveled is not a state function, while elevation is. And this is important for chemistry because maybe you want to do a process that gives off lots of heat or gives off lots of work and little heat. If you are trying to drive a car and you are combusting your gasoline, if all it does is give off heat, then that's not a very effective vehicle. Instead, if you're able to convert that gasoline into lots of work, you're going to get a high gas mileage. And you're not going to burn out the different components of your engine. And so that's a very effective process for what you want to accomplish. But you could imagine scenarios where you want the opposite, where you want to give off lots of heat and not do a lot of work. So it's important for chemists and scientists to understand how to manipulate the process to get the desired end product. Here's just an example of how in chemistry we can have different paths to take. And depending on what we want to get done, we might take path A or path B, and that will affect how much heat or work is done or absorbed. There's another term that we use in chemistry for heat called enthalpy. And enthalpy and heat are the same when we're doing reactions at constant pressure. And almost all chemical reactions that we deal with on the basic level are at constant pressure. And so what that means then is that we can simplify our calculations and just talk about heat or enthalpy interchangeably. This equation was given to you in the ebook, and it tells you that energy, the change of internal energy, is related to the heat and work that are done by a system. If the heat's at constant pressure, then that's equal to enthalpy. And the reason why this is important is because enthalpy is a state function, which means that it's a lot easier to deal with processes and relate one chemical reaction to another because they can be path independent. This is just another way of looking at work, talking about the volume that's displaced, done at a certain pressure. And since for most chemical reactions that we'll deal with, the volume displaced is close to zero, this term typically goes to zero. And so what we can do then is we can simplify and essentially just talk about the change in internal energy as being equivalent to the change in enthalpy or heat. And we can measure heat. We have lots of different ways of measuring heat. The last concept to talk about today is the sign of enthalpy. And there's two terms that we talk about, endothermic and exothermic. And when you are exiting a building, we use that term exit versus enter. And so it all is related to heat, and it all is based on whether or not the heat is entering or exiting the system. If we have our system and it's giving off heat, the surroundings gain heat, they get hotter, we see an increase in temperature of the surroundings. Or if we have a thermometer, it might go from, let's say, 10 to 50 degrees Celsius. The opposite process, an endothermic reaction, is one that the system gains heat. The surroundings lose heat, and so we observe a decrease in temperature. The thermometer goes from 50 to 10, let's just say. And so when we observe changes with our thermometer in the laboratory, we're really looking at that from the perspective of the surroundings. And so it's important to take a step back and think for a moment whether the reaction is endothermic or exothermic. Okay? Let's try a problem here. Consider a process in which a system loses heat and performs no work. The amount of potential energy remains the same. Which statements are true? So how do we want to think about this? Let's start by breaking down the prompt part by part. We first see that the system loses heat. So we know that Q is less than 0. It performs no work. Okay? So since it loses heat, the sign of Q is negative for this process. Since we know that it performs no work, we can relate this to the change in internal energy. We know that the change in internal energy is equal to heat plus work. Since there's no work, then it's just equal to the heat. And since the heat was released, it went down, the energy, internal energy, must also go down. Finally, how do we evaluate this last part? Well, we know that that total energy, or internal energy, is the sum of kinetic and potential energy. We're told that the potential energy is constant. And since it's constant, but we know that total energy must go down, then the kinetic energy must have decreased, which means that the system lost kinetic energy. And that means that all three claims are true. So that's it for today. If you have questions, ask on Piazza or come to office hours. Have a good day.